Hello everyone, welcome to a short video on the improbable journey of detected photons. We will be discussing a probabilistic model of light propagation in which scatterers are treated as particles, photons are treated as particles that bounce off of the scattering particles. And the path of such photons is a series of propagation steps then without interaction, followed by a collision with the particle and redirection, followed again by a step without interaction and a collision, etc., etc. Such photons continue until they are detected, or they can disappear through absorption. So we can now ask all kinds of probabilistic questions like what is the likelihood of a given photon path, or what is the distribution of path lengths between collisions, or what is the probability of absorption given along a given photon path, etc. Before we go there, first we will brush up some of the ways to describe probabilities, namely the probability density function, PDF, the cumulative distribution function, the joint probability density function if we have two or more variables. We'll discuss moments of the PDFs like expected value and variance, and finally some notes on transforming PDF. First, consider a random variable x, which can take values in the interval x minimum to x maximum. Then the probability density function p of x is defined in such a way that px times dx is the likelihood of the random variable falling in the interval between x and x plus dx. The probability density function is normalized on this domain so that there is unit probability is 1, that the random variable will fall at some point within this interval. An example of this is the PDF of photon step length between interactions, so the free propagation between interactions, which has a unit of per length because it describes the probability per unit length. Next, we define the cumulative distribution function, capital P of x of the random variable, which gives the probability, so the pure probability, unitless, of this random variable falling somewhere between the minimum of the interval, x min minus, and a certain value of x. Of course, the cumulative distribution function is then related to the probability density function through this integral relation. So the cumulative probability is given by the integral from x minus to x of the probability density function. And a short note here, alternative notations for the cumulative distribution function are given as here. If we have two variables, two random variables, we can define a joint probability density function, p of x and y of these two random variables, where again x and y can take values on their respective bounded intervals. And then the definition is analogous. So p of x and y dx dy is the likelihood of the random variable x falling between x and x plus dx, and of the random variable y falling between y and y plus dy simultaneously. To this, PDF is normalized on the domains, on both domains, so the double integration yields unity. And an example of this we have already encountered. It's the phase function. The phase function is the joint probability density function of the polar and azimuthal scattering angles theta and phi. Remember that the domain for theta was from 0 to pi and for phi was from 0 to 2 pi. So this joint probability density function then has units per radian squared or equivalently per star radian. From this joint probability density functions, we can calculate the so-called marginal PDFs, P of x and P of y, which are derived by integrating over the domains of the other variables. So the marginal probability density function P of x is found by integrating over the y domain, and the marginal PDF P of y is found by integrating over the x domain. So let's look at a phase function example. Take the Rayleigh phase function, again the joint PDF for polar and azimuthal scattering angles given by this equation. You'll note that on the left hand side we write this specifically as a joint PDF, even though on the right hand side there is no explicit functional dependence on phi. So to compute the marginal probability density function for theta, we integrate over the phi domain, which in this case is straightforward, just adds a factor 2 pi. And in order to find the marginal probability density function for phi, we have to integrate over the theta domain, which takes a little bit more work. But in the end, we'll find that P of phi is a constant, 1 over 2 pi, which means that the angle phi is uniformly distributed over the domain from 0 to 2 pi. Here we have also the special case of two independent random variables. So the joint probability distribution P, theta, and phi can be written as the product of the probability density functions of both marginal probability density functions. We can calculate some descriptive parameters from PDFs. For example, the expected value of the random variable defined as such. So it is a weighted sum of the values of x weighted by the PDF. The expected value comes with some rules. So if we multiply it with a constant c, the expected value gets multiplied with a constant c as well. If we have two random variables x and y, then the expected value of the sum equals the sum of the expected values. We can also calculate higher order moments, which are defined here. So the eth order moment is given as the weighted sum of the variable x to the power raised to the power of I. So the 0th order moment, in this case, x to the power 0 is 1. So this gives us back the normalization property of the PDF. The first moment we just calculated is the expected value or the mean of the probability density function. The second order moment is given as the expected value of x squared, etc., etc. Special note for the variance as a descriptor of a PDF. So the variance of a random variable is defined as the mean squared derivation around the mean value of the distribution. So in the notation of the previous slide, that means that the variance of x, or symbol sigma squared, is the expected value of x minus the mean, the first moment, squared. So we can work out this square between the brackets. So we get the expected value of x squared minus 2x m1 plus m1 squared. Then we can apply the sum rule of the expected values to in the third line, and then finally combine things again and write the variance then as the expected value of x squared minus the square of the expected value of x. So this now expresses the variance in moments of the probability density function. The variance comes with some rules as well. If we have for scaling, for example, if we have the variance of ax plus b will equal a squared times the variance of x. And if we have two variables x and y, then the variance of the sum will be equal to the variance of x plus the variance of y only if the two variables x and y are independent, uncorrelated. Otherwise, an extra term arises. Finally, let's look at the transformation of PDFs, and we'll do that by an example. So suppose we have a complex random variable, z is x plus I times y, and we know the joint probability density function for x and y, p of x, y. So now let's say that for this complex variable, we want to know the distribution of the amplitude and phase instead of x and y. As you know, you can represent a complex number as a vector in the complex plane. So it has an x and y components corresponding to the real and imaginary part, but you can also express it as the length of the vector a and the angle phi with the real axis. So the question is how to transform the known probability density function p of x and y to a new one for amplitude and phase. This is how it is done. So we can express the new probability density function as the old one times the determinant of the Jacobian matrix, the transformation matrix. So this is the matrix that contains all the partial derivatives to from one domain to the other. And since we have a two-dimensional domain here, x and y, or theta and phi, we get a 2 by 2 matrix. So for complex numbers, we can actually calculate this determinant because x equals a times cosine phi and y equals A times sine phi. So if we then calculate the partial derivatives and calculate the determinant, it yields simply that, this is equal to A. So the final expression is that the new probability density function P of A and phi is given by A times that of P, X, and Y. So now let's pick a form for the joint PDF of P of X and Y. Let's suppose it is a normal, joint normal distribution as given here. So now we wanted to know the distribution of amplitude and phase, A and phi. So we can write first the expressions. A equals the square root of x squared plus y squared, and phi equals the arctangent of y over x. And with the previous results that P of A and phi was equal to A times P of X and Y, we can now write that the joint probability density function of A and phi is given by the last expression over here. Actually, this is not a coincidental example. This is the actual joint PDF of the amplitude and the phase of the electric field in a speckle pattern. A speckle pattern, for example, you can generate when you point a laser pointer to a granular wall. What happens is that the electric field scattered back from the wall has different amplitudes and different phases due to the roughness of the wall, and they will constructively interfere, destructively interfere, everything in between. So you will observe a granular pattern. This then is the distribution of the amplitude and phase of that resulting electric field. So we can calculate, for example, the marginal distribution for the amplitude of this field, which means that we have to integrate over phi. Again, in this case, it's simple because there is no functional dependence of phi in the expression. So the marginal distribution for the amplitude becomes as given here. Now we can ask ourselves if we can also derive the PDF for the measurable quantity, the intensity being equal to the electric field amplitude squared. Yes, we can. That means we need another transformation from A to A squared, which means that we have to calculate another Jacobian, which is in this case one-dimensional, so that is straightforward, 1 over 2A. And it means that we can now write the probability density function for the intensity in this speckled pattern as follows. We could take a very brief sidestep to calculate the first moment, or the average intensity from this distribution. And if we perform this calculation, in the end we find that the average intensity, so on the term on the left-hand side, equals 2 times sigma squared, the term on the right-hand side. So we can make this substitution back into the middle equation and finally get for the probability density function of the intensity in the speckled pattern this simple expression. So it is only governed by the mean intensity in the pattern. This sets us up to actually look at this improbable journey of detected photons. If we want to calculate the probability of a single path, so a photon enters the tissue, has a free propagation to scatterer number 1, is scattered there, then a free propagation to scatterer number 2, where it is scattered again, etc., etc. We can calculate the probability of the single path as the product of all the independent steps that make up this path. So we can write the total probability as the probability of a length L1 without interaction times the probability of being scattered at the location of scatterer number 1, so let's call it R1, times the probability of scattering from the direction, the original direction S1 to the direction S2, so pointing to scatterer number 1 to pointing to scatterer number 2, etc., etc., etc. After that follows another step, then another collision, then another change of angles. So we can write the probability of the single path as this chain of. So now consider the situation where a fiber is placed at location A, which launches photons into the tissue, and another fiber is placed at location B, which is used to detect the photons. We can then state that the detected signal will be proportional to the probability that photons launched at A will be detected at B. So we need another rule to calculate that total probability, we need to add the probabilities of all possible photon paths leading from A to B. So the total probability is the sum of all these paths. And then the probability of a single path in that sum, again, equals the product of all the independent events that link that particular path. So the question is, can we find analytical expressions using this approach? In some cases we can. And of course, finally, this is exactly the reasoning behind Monte Carlo simulations, trying to simulate as many random photons paths as possible, so that in the end we actually calculate the probability that photons launched at A are detected at B. And so in the end we calculate the detected signal. But that's for later.